This is our last video in the unsaturated hydrocarbon series. Primarily today we will be talking about aromatic compounds, how to name them, as well as some of the different structures that they will have and some of the uses of them. So up until now we've been dealing with some cyclic compounds, but also straight chain compounds. Today we're going to be talking about something special. These are special cyclic compounds. They're called aromatic. Aromatic compounds will be compounds that have an alternating double bond pattern to them. So it will look like a cyclic compound, but because of this alternating double bond pattern we see, it's going to have all sorts of special properties and behaviors to it that we actually give it its own functional group. So we call these aromatics. The smallest aromatic compounds will be those that contain 6 carbons. Okay, so this compound right here is called benzene. And they have low hydrogen to carbon ratios because of this alternating double bond. Okay. Aliphatic compounds are going to be aromatic or organic compounds that are not aromatic. So that's everything else we've learned so far. Okay, so all of those are aliphatic. If it has this alternating pattern, this alternating double bond pattern, then we call it aromatic. So up until now, right, this would be our expanded structure. You're starting to see line angle structures that look like this. I want to talk about these line angle structures a little. So benzene is kind of a unique structure, and what we end up doing is when we have these more complex organic structures, we stop drawing the C's and H's because C's and H's are in everything that have organic compounds. So we start kind of doing shorthand with them. So what we do instead is we draw a line, and at the angle of each line, so the bend in the line represents a carbon. So there's a carbon here, and 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 a carbon here. We don't draw the hydrogens bound to the carbon at all. It's understood that you can look at this and say, okay, there's a carbon here, and it has 1, 2, 3 bonds, which means it needs one more hydrogen, which is hanging out here. It's understood that you know that that hydrogen has to be there, even if we don't draw it. So in a benzene ring, the other thing I want to talk about is because of this special alternating double bond pattern, these two structures are equivalent to each other. Even though it looks like the double bond rotated through, it's because it can, and it does. It's constantly rotating around, but it keeps this on-off pattern. So sometimes you will see benzene drawn like this with just a circle in the place, and this is to represent that that alternating double bond pattern is rotating through the molecule. So when we look at a benzene structure, each of the carbons is going to be sp2 hybridized because it has 3 bonds, 1 hydrogen, and then 1 bond here, and another bond here, or a electronic group here, electronic group here, and an electronic group here. So 3 electronic groups. S, P1, P2. 1, 2, 3 electronic groups. Because of this sp2, it has 1 unhybridized p orbital on each carbon. And that 1 unhybridized p orbital in each carbon is how we end up getting that alternating double bond pattern. As we can see, there's 1 on each carbon, so these 2 can overlap, then these 2 could overlap, and these 2 could overlap. Or these 2, and these 2, and these 2. So it can alternate, and it does alternate. So instead of having it be singular, we kind of end up with these 2 rings. We call this delocalized pi bonding. But basically, it's kind of this nice kind of like circuit of the pi bonds being shared. So which of these would best describe this molecule? Best answer here is aromatic because it contains a benzene ring. Remember, aliphatic is everything else. Now, we do have some special names that we give to compounds that have a benzene ring attached to them. So when we have a single hydrogen attached to a benzene ring and one of those is replaced with something, we give it a new name, but we still keep the word benzene with it. So we could have ethylbenzene, nitrobenzene, bromobenzene, chlorobenzene. These all seem relatively straightforward. They can get a little more complex. Some of these have common names as well. The IUPAC names are accepted, but sometimes if like you work in a pharmacy or something like that, you will actually end up using the common name more than the IUPAC name. So instead of saying methylbenzene, oftentimes you will hear toluene. Instead of hydroxylbenzene, we would call this phenol. Aminobenzene is actually called aniline. And instead of this being, which we'll learn later would be an ethanoic benzene, we call this benzoic acid. And so we'll talk more about this one much later. But we already kind of saw these alkyl groups on other things, so just understand that sometimes these have different names. I would encourage you to throw these on a flashcard if you're struggling with naming them. So how do we treat a benzene group when it's kind of one of those alkyl groups? So we don't call it a benzene anymore. When it's an alkyl group like this, right, here's our long chain, and we're adding it on as kind of like a substituent group, we call it a phenyl group. Okay, so a phenyl group would be, in this case, we have 1, 2, 3, 4, 5, 6, 7 carbons. So we're going to have a heptane because it's all single bonds. So it's A and E, heptane. And we count 1, 2, 3, 4. 1, 2, 3, 4. So it's going to be 4-phenyl heptane. Now, sometimes the benzene group is written out in a condensed form like this. Benzene by itself is C6H6, but we know if it's going to be attached to something that we would have to get rid of one of those hydrogens to attach it. So C6H5 is a benzene group, which we call a phenyl group. So in this case, we have cyclobutane, and now we're going to have 1,1-diphenyl cyclobutane. The last thing we need to talk about with this is when we have two groups attached to our benzene ring. And these are often denoted by ortho, meta, and para naming systems. So we would always consider one of these to be the one position. So if we're 1, 2, this would be ortho dibromo. If we're 1, 3, we would be meta dibromo. If we're 1, 4, we're para dibromo. Okay, so we use O, M, and P. Obviously, the 3 could be over here, or the meta could be here or here, right? This could be 1, 3, this could be 1, 3. Saying 1, 2 dibromo or O dash dibromo are both acceptable ways to do it. You should just be aware that this is a way that we often name benzene rings. When two or more groups are attached to the benzene ring, right, their conditions can be indicated by their number, but we want to make it the lowest possible number as we've done before. So here we see the meta orientation, the 1, 3, so we could write it as meta bromo chloro, B comes before C, benzene, or we could say 1 bromo, 3 chlorobenzene. We don't have an orthometa-para once we go bigger than 2, so now we would have 1, 2, 4 trichlorobenzene. Or we could have 3, 5 dichloro, and then if we took the chlorines away, we would be back with a benzoic acid again. So 3, 5 dichlorobenzoic acid. So which of the following could not be included when we were naming the system? What would we not say about this? We have no phenol group. Remember, the phenol is where we have an OH. So we have a phenyl. You could make the argument for that. Phenol, OL, is where we have the OH group on it. You could say this is a benzene, and we could also say that this is an aniline because we have the NH on the benzene ring. So all of these are potentially good names for it. This one has no place in this compound. What prefix would we use to describe the relationship between this this methyl group and this chloro group? This would be ortho. 1, 2 is ortho. 1, 3 is meta. 1,4 is para. So I want you to take a moment, pause, and go through and try and name these compounds on your own. All the same rules we were using before in terms of metheth, probute, counting, having lowest number possible, all of these still hold true. So in our first compound, there are two different names you could have for it. 3-ethyltoluene, or you could say M-ethyltoluene, right? 3, if we didn't have this group here, this would be toluene. So if you had 3-ethyltoluene, you would properly describe this. You could also say 1,3, right? We have this 1,3 kind of orientation here, which would make this ortho is 1,2, 1,3 is meta. So that's how we end up with meta-ethyltoluene. Now, note that the 3-ethyltoluene, the methyl group, which is part of the toluene structure, is being assigned as the 1 position. Okay? So what we mean by that is, if we got rid of this guy, this would be toluene. So we're counting this existing methyl group as the 1. In the next one, we could call this propylbenzene or 1-phenylpropane. So let's look at both of those. Propylbenzene. Here's my benzene ring, and here's a propane group off of it. 1, 2, 3. Propylbenzene. Or we could say this is my root, so I have propane, and there's a benzene group on it. So this would be 1-phenylpropane. Both of those are acceptable. And lastly, when we have 3 groups around the ring, we have to arrange them in a way where the numbers make sense. So we have 3-chloro, 5-ethyl, benzoic acid. If we get rid of both of these groups, we're left with benzoic acid. We figure that this will be the 1 position. 1, 2, 3, 4, 5, so the 3 and 5. We want the chloro and the ethyl, and we go by alphabetical order. So chloro would come first. C comes before E, so 3-chloro, 5-ethyl, benzoic acid. So we want to talk about some of the physical properties that are associated with aromatic compounds. Just like all the other hydrocarbons, they're nonpolar. They're predominantly made of hydrogen and carbon. So again, they're going to be nonpolar, which means they're not soluble in water, which means we consider them hydrophobic. Because the aromatic ring, that special pattern of the alternating double bond, single bond, double bond, single bond, they're very, very stable. And oftentimes the aromatic portion of the ring won't break. So we're not going to have an addition reaction like we see with other alkenes. Right? We know in addition reaction, we break the double bond apart and we add something across the double bond. That won't happen in an aromatic compound. The aromatic compound, the double bonds in the aromatic compound are very, very stable. They will resist going through an addition reaction. Sometimes what we will see happen and how we get things like this is the hydrogens on the ends will be replaced by something. That's how we get these decorated aromatic rings. So sometimes these aromatic rings can kind of be added to each other like Legos. They kind of stack on top of each other. And so we can get these really big structures. We'll start seeing more of these kind of structures when we get to biochem. These are very similar to what steroids, natural steroids in our body and things look like that. So we'll see much more of these kinds of structures later on in the semester. But they just stack together and they still maintain an alternating double bond pattern. So we have naphthalene, benzopyrene, dibenzothiazanine, sorry, I can never pronounce that one. Typically when we start getting these bigger compounds, these are often considered carcinogenic. Now that's not to say a steroid is carcinogenic, there's a lot more going on than just this base structure. But these types of bigger aromatic compounds, these polycystic, many cycled aromatic compounds, typically are carcinogenic. So, benzene and toluene are some of the very popular aromatic compounds that are used in a laboratory, and they're really good nonpolar solvents. So, right now we know that water is one of the best polar solvents around, but that doesn't help us when we have nonpolar compounds. What if we need to dissolve a nonpolar compound? Benzene and toluene, which are both aromatic compounds, are really good at being these solvents. They're also really important in our diet. So amino acids and other vitamins that we have to take to kind of be functional have aromatic compounds in them. So here's benzene and toluene, phenol, but then we start getting into things like aniline, styrene, phenylalanine, and here's riboflavin. This is an aromatic compound. This is basically what vitamin B2 is. So aromatic compounds are the whole range of interesting solvents all the way to essential vitamins that we need in our body. Which of these aromatic compounds is the original active ingredient in mothballs? This is more of just a kind of trivia type question. So the original one is naphthalene. Naphthalene is actually pretty much what mothballs are. So if Grandma and Grandpa ever smelled like mothballs, what you're probably smelling is the naphthalene. This concludes Chapter 12. At this point, you should be working on your homework. It's really important that you practice these. The homework does allow you to, draw in the homework within OWL, but I really encourage you to draw these on paper and practice drawing them on paper. More worksheets will be going up for practice on doing different ways to draw Lewis structures. If you need to go review your Lewis structures, I strongly encourage you to do so.